This is my fourth time trying to record an opening and I don't know what to say. I have a project, it had a goal, this is what the project was meant to do. It's whatever's in this image. Uh, the first main thing is this list up here. So I wanted to be able to provide a list of satellites with varying parameters and have all of them be created in STK. The second thing I wanted was to be able to compute all the access windows fairly easily. Both of these tasks were very easy, and almost all the code necessary to do this is provided in the code snippets on the official AGI website. I highly recommend going through this if you have any projects that you would like to try out relating to the software and would like to get your hands dirty a little. For this specific project, the goal that I wanted to extend on was the attitude goal, which is while the satellite is in an access window, I would like to have the satellite point towards a ground station. More specifically, point its sensor along the ground station and follow it to simulate a communication system of sorts. Obviously, I'm not very familiar with communication systems, so actually computing that stuff is not something I can do, but it is a starting point that will be explored further on when the semester starts and I can find the appropriate people to help me out. So those are the goals of this project, is to have this satellite point its sensor towards the ground station across the orbit without any fail. I'm aware that you can do this by using a pointing model in STK. However, I was trying to avoid that simply because I want to get the file that creates this attitude. I want to get the attitude file, and then from there, one of my research goals is to actually try and model a control system, and this provides the desired attitude, which is the information I'm trying to extract. So without further ado, let's begin the code digestion. As you can see, I've tried to do this before. It has not worked very well. So the first piece of code is to launch SDK. This is copied straight off their website. It goes into your computer, grabs the file, the necessary applications, runs it, makes it visible, etc., etc. The next main thing is to create a scenario. I've just been naming them solid out of consistency, you could say, and you can set the start and stop time here. I've limited it to 7 hours because any longer and my computer starts running a bit slower when it tries to create the attitude files. 7 hours is usually enough to get several windows, but not long enough that it can cause any problems with my computer. The first main thing is to create a facility. This is pretty straightforward. All of this code is copied straight from the website I showed you guys earlier. You assign it a position, give it a color, and it will create the facility for you. The first main thing is to create a sensor for this facility. So as you saw in the drawing, our goal is to create a semisphere to show that the ground station can communicate with anything within this sphere, assuming that we point the ground antenna in the right direction, but that is a concern that isn't necessarily for us. So to do this, we would have a simple conic pattern with a half angle of 90 degrees. This, if you build the intuition, you will know instantly this is a half sphere. Next up, we have the range constraint. This isn't necessarily accurate. As I mentioned, I'm not very familiar with control system stuff, so I've been setting the range to 1500. I'm not sure if this is too much or too little, but it's something that you should all take with a grain of salt. Next up, we have to do some graphics things to make sure that the sensor uses the constraints provided to it. This isn't necessarily relevant to the range constraint, but if you have a angle of elevation constraint, then you would need to run these two lines to ensure that it displays that constraint. The next thing that we're making here is the satellite. So we're making a satellite. This is based on the CubeSat mission that we are trying to model. And once again, this code is copied straight from the website. A bit of modification was made because we tried to use eccentricity rather than semi-major and semi-minor axis rather than apogee and perigee, but the overall process is the same. We have a list of orbit parameters, and a future goal is to actually just turn this into a function so that it's very easy to run over a list. This is a project that I have been working on as well, but it is not ready, so I cannot show you guys that it works yet. Once we have this done, we would simply propagate the satellite's orbit and set it in motion. Another thing that we do is we just change the model to a 3U CubeSat. This is just for consistency's sake. And yeah. The final thing is to add a sensor to our satellite. This was the trickiest one, actually. As you can see, it's the same command from before, except we're using a half angle of 1 degree. I've searched this up as well, but I cannot make sense of it. It means this angle right here is 1 degrees. A lot of people have told me that this is very small. I have no reference, so for me it's correct. Also, I chose 1 because if this file works for 1 degree, then it should work for all the others. And the other command is to align the sensor with the x-axis of the satellite's body. As you can see, there's a connect command down here. This connect command was the original way that I was using to do it. However, I figured out, or rather, the AGI support team sent me the data providers that I needed to go through and change things on my own. Sorry, not data providers. They sent me the help files. I will leave that for a different video, but it is not very difficult to go from a connect command to the appropriate MATLAB command. And finally, we also set the range of this sensor. We set it to just 1 more so that when the access is made, it's not at the very edge of the sensor, rather it's a kilometer past it. And this doesn't make much of a difference, but it was something that irked me when I was trying to test. And finally, we also have the constraints for the sensor. The final thing that we do is we compute access between the satellite and the sensor of the facility. And this is done with these 2 commands. It's pretty straightforward. Once again, copied straight from their website. This interval is the maximum time step that we will be taking in seconds when doing our attitude file. This is 0.1 seconds, so 100 milliseconds. Finally, we have the root.rewind. This just resets the animation. And if we run this file, I will minimize both of these. We can see that it opens SDK, and it has named our scenario. And very soon it will set the animation time, add in a ground station, give it the appropriate sensor, add in a satellite, add in its sensor, and finally propagate its orbit. And as you can see, the sensor is very thin for the satellite. Let me zoom in so we can get a good view. There it is. So it is a very thin sensor, and we can trust that if this sensor can lock in on the ground station, then any sensor should be able to do it. So that was the first command. The second file that we care about is the attitude file. So this is the function that will create the attitude file. As you can see, it's going to be computing the Earth-centered fixed frame vector. That's why I named it ECF. And it will take in an input of a satellite, a facility, the axis between them, the scenario start time, the interval for interpolation, and it will output an attitude file in the same folder with this name. As you can see, I've been running it before, so the file is right there. And the way that we are going to do it is first we're going to get the relevant access data. We're going to interpolate between that access data at the interval specified, and get a pointing vector for each and every point in that interpolated time. And finally, we will create the attitude file, iterate through everything, and load that data into the attitude file, and that will create our attitude file. So This is the command. These are the commands for getting access data. Once again, this is copied straight from the MATLAB code snippets. Finally, we have this pointing data. This is a unique file that I have made, which is its own function, GetPointingVector, and I will go into it once I am done here. So the first thing we have to do for the attitude file is to specify some preliminary information. Things like the version of SDK that we are beginning the attitude, the number of points that we have, which is given by count. Believe it or not, count will come from the length of the time vector that we get. We have the scenario start time, blocking factor, interpolation order. By default, this is set to 1 to have first order interpolation, but for the case that I'm using it, we didn't want any interpolation. We wanted the satellite to only point when we told it to point and never interpolate in between. Finally, we have the central body, which is the Earth, and the coordinate axes, which are fixed, the time format, which is UTCG, and we have the type of data that we are feeding it. We are feeding it in the Earth-centered frame vector. And finally, to add our data, we would iterate through the times that we have, and for each time we would have the 3 components of the vector, the x, the y, and the z. And once all these are written in, we can end the attitude file, close the file in MATLAB, and load the data into the satellite of our current scenario. So now we have to go back to this, which is the GetPointingVector. The GetPointingVector is its own function. This function takes in 2 objects, the 2 objects that you would like to compute the vector between, the start array and the stop array, which are the list of start and stop times respectively, as well as the interval, which is the time in between, which is the time step between any 2 points. The output, it will give you a list of times which it interpolated in the access windows, as well as the pointing vector at each of those times. So the first step is to obviously interpolate your times. This is done with this function, interpolate XS. This is its own function. This function simply takes in a list of start times and stop times, as well as the interval, and it outputs the times in between. So suppose you have an access window between, let's say, 1958 and exactly 20. Right, so it's between 7:58 and 8 p.m. And let's say the interval is 10 seconds. Well, we'll start at 7:58, and every 10 seconds it will create a interpolated time, and at each of those times it will get the vector for which way the satellite has to point. This interpolate XS just does the interpolation for you. MATLAB has a lot of date-time support, so it's very straightforward trying to get this data. We just have to make sure that we have the right amount of data. And that's where this CountTime command comes in. So what this CountTime command does is you feed it the start and stop array, as well as the interval, and it will do a preliminary count of how many points you are expected to have. That is this right here. And you can, as you would expect, this one's pretty straightforward, right? You would take the start time and the stop time, find the difference between them, convert that into seconds, and then figure out the maximum value, which would be the ceiling of that value. And then you would add that to the previous number and subtract 1 at the very end because it creates an extra point for some reason. Each count vector is also of importance to us. So this each count vector keeps track of how many points are in each access window, which is something you would have to keep track of if you have a lot of access windows. So finally, once we have the number of points and we've created the full length of the time array, the time vector, we would simply iterate through all the start times and stop times, interpolating in between. This is time start, so this is the first point that you were expected to have. This is the time stop, which is the last point you're expected to have. And the points in between are simply, counting between your start time, your stop time at the intervals. And this should be it. This is It's a bit weird to have to deal with all the date time functions of converting, your array into a date time and then performing arithmetic on it, as well as assigning those values around to each other. But this is a good exercise to get used to handling weird data formats. Yes, so once we have this, we have GetPointingVector. So for the GetPointingVector, once we have a list of times that we would like to have our pointing vector over, and the count of how long each access window is, we are able to create the full pointing vector, which is going to go through each of these times and figure out where the satellite has to point at each time. As you would expect, this is just the sum of all the access windows. One more thing I just want to mention, that there are 3 points because of x, y, and z, as we would expect to have a 3D pointing vector function. So the next thing is we just have to go through each of the access windows, which is the length of each count. For each one, we have a start interval and a stop interval. So the first one, we would have to go through the first n points. Then we would have to go from the next number of points that we have to deal with, then the next, then the next, then the next. For each of these values, we have to use a data provider to get the Cartesian position. For the satellite, it'll be object 1. We will get the Cartesian position in fixed. And for object 2, we will get the Cartesian position, which is by default in fixed. As you can see, there are connect commands here. These commands perform the exact same thing. There's just a little bit more formatting that has to go in because the output comes out as a string, or a cell array rather, and you would have to filter out the data that is relevant to you versus not. Having connect commands is entirely possible. It's just that your program will run much slower. And once you have the position data for the satellite and the facility, taking the difference gives you the relative pointing vector, which is what this function does. And as you'd expect, we would have to go through each start and stop interval and put that data into our pointing vector. And from there, we will have our pointing vector, as well as a list of times that this pointing vector acts over. So let's run the file. This is the attitude file in the ECF frame. I ran this earlier just to make sure it worked. As you'd expect, you'd have to feed it the scenario, the first object, which is the satellite, second object, which is your facility, the access between them, and then the start time and the interval. And when we run this, we can see that it's creating the, get pointing VAF, ECF line 30. Was I accidentally typing? Ah, yes, I was accidentally typing in here. There we go. Yeah, my apologies. So now it's going to be creating the attitude file. As you can see, it ran very fast, largely due to the fact that the data providers are very quick to get data, versus for the connect commands, you have to iterate through one at a time, which you can imagine is much slower. We can actually view our attitude file here. And yep, this is the attitude file. So this tells you that, okay, at this time, the satellite must point in this direction. This time, it'll point at this direction. And they're all at, 100 millisecond intervals all the way down the list. And it starts at our start time. This is the number of points we have, which is almost 16,000. And I've been running this file for a very long time, so if we go down to about 3,000, let me see if I can speed it up, 3,811-ish, we'll see that that is where the change occurs from one access window to another. Let's see, there it is. Let me go back up a little. Yep, right there. So this is the last time for the first access window. From there, there is no attitude data loaded in. up until the next axis window opens up. And so the satellite will actually stay pointing in this direction in the Earth fixed frame until this time where the next data point is loaded in. And so now if we go to the satellite ourselves, we can see that for the first hour and 40 minutes, we would expect no access window. However, at 1:40, when we cross into our ground station, we would expect the satellite to point straight at the ground station. And there it is. And we can see that it's staying relatively focused there. The time step of 100 milliseconds is actually pretty small. And so what appears to us as a smooth line it's a very smooth transition actually. If we were to decrease the time step though and zoom into the ground station, we can actually see the jittering of the thing. There it is. So this is because it is in fact a discrete system. If we were to decrease the time step again, we can see it now, like it's very clearly jittering back and forth. But this is happening every 100 milliseconds. So for a normal simulation, this is, for a normal simulation with the time step of, in the 100 milliseconds, it's a very smooth transition. And as you can see, it's this 1 degree half cone angle sensor is staying very well fixed on to our ground station. So we can see that we have nothing to worry about. It is in fact doing its job. And, if an actual attitude system were based on this, assuming we had the orbit and ground station perfectly known and the sensor was also perfectly in line, we can see that it does in fact work. And let me zoom back to the satellite. Yep, and it's still following it. And as we leave the ground station sensor range, we can see that the sensor will start to deviate from its target. Let me zoom out a little bit just to let us see it more clearly. There it is. And so you can see once we leave the ground station, we start deviating immediately as the Earth fixed frame rotates underneath the satellite. And as we would expect, this may seem like it's moving, but in fact, in the Earth fixed frame, it is not moving. It is pointing in the same direction. And if we were to speed along up until the second time window, which is at 3:18, let's see, there it is. Whoops. So the sensor persistence is a bit of a problem. This is something I haven't figured out programmatically, but there is a way to do it. However, we can see that our satellite is in fact still pointing at the ground station. It's just the sensor isn't persistent, so there's an issue. That is something that can be fixed pretty easily. It's just I haven't figured out how to do it programmatically yet. So I believe if we go into 3D graphics, project to use range constraint and apply, there it is. So that's just something I'll leave in the documentation so that someone can recreate it. But as we can see, it still focuses on the ground station. No real issues there. And so yeah, that's where the clip was from. This is the project. As you would expect in the future, we're not going to stop here. We're going to see if we can try to implement an actual control system. So right now the MATLAB script gets the exact vector between the position of the satellite and the position of the facility, and then creates a vector right in between the two. However, further down the line, we would want to implement some sort of rigid body dynamics and load in that file, which is what we'll be doing further, which is what I'll be working on later. And with that, that is the full tutorial. That is everything that this is. Thank you for watching.